Hello everyone. Thank you for joining today. I am Soumyadeep Seth, an assistant professor in mechanical engineering at IIT Gandhinagar, where I started in June 2021. Today, I will be presenting the poster on one of my postdoctoral works at the University of Illinois at Urbana-Champaign. I will be talking about coalescence-induced droplet jumping. Coalescence-induced droplet jumping has attracted significant attention over the past few years due to its fundamental relevance in understanding dynamic droplet interactions. Such jumping droplets have been used for several applications, such as in enhancing condensation heat transfer, anti-icing, thermal diodes, electrical energy harvesting, electronics cooling, and self-healing, and so forth. In particular, it has been experimentally demonstrated that jumping droplets can lead to 25% higher overall heat flux and 30% higher condensation heat transfer coefficient as compared to state-of-the-art hydrophobic condensing surfaces. When small droplets coalesce on an ultra-low adhesion nanostructured superhydrophobic surface, the excess surface energy is partly converted to kinetic energy, leading to jumping of the coalesced droplets. The nanostructured surface beneath the coalescing droplets reduces the droplet adhesion to the substrate by minimizing the solid fraction and breaks the symmetry of the coalesced droplet. As a result, the droplet accelerates and departs perpendicular to the surface, where the jumping velocity can be closely related to the removal efficiency of droplets from such surfaces. Most of the experimental results found in literature relies on coalescence-induced jumping of condensate droplets. This, however, has several limitations, such as uncontrollable droplet radii, unequal sized droplets, and interference from surrounding droplets. Furthermore, condensate droplets coalescing on the surface prior to departure must reside in the focal plane of the camera to be able to accurately measure the initial droplet radii and jumping velocity. Here, in this work, we present a novel method of studying jumping behavior of coalesced droplets by dispensing droplets from the piezoelectric dispenser. We study a wide range of droplet radii and their jumping velocities. For coalescence-induced droplet jumping, nanotextured superhydrophobic surfaces were developed. Copper oxide nanostructured surfaces were created on commercially available copper tabs by immersing them in a caustic solution maintained at 90 degrees C, leading to the formation of sharp knife-like structures of copper oxide. To functionalize the surface, a silane was deposited using vapor deposition. The low surface energy of the silane, HTMS in this case, along with copper oxide nanostructures, makes the surface superhydrophobic. To study droplet jumping, we interfaced a high-speed camera with a frequency-controlled piezoelectric droplet dispenser. By utilizing the piezoelectric dispenser to feed microscale droplets to a larger droplet at a prescribed frequency, we could create variable sized droplets on any surface by modulating the piezoelectric droplet adhesion frequency. To grow droplets, the piezoelectric dispenser was placed above our superhydrophobic surface with a spacing of about 5 to 10 millimeters and turned on to dispense microscale droplets. After the first drop grew to the desired radius, the location of the piezoelectric dispenser was quickly shifted by using the horizontal stage control so that a second droplet can be deposited right next to it. Both equal and unequal sized droplets were dispensed from the dispenser to measure the jumping velocity of the coalesced drop. Once the two droplets come in contact, a liquid bridge is formed that is accelerated radially from the point of contact due to curvature difference. After coalescence, part of the excess surface energy converts to kinetic energy, causing the merged droplet to jump. The location of the droplet at various time instants allows us to calculate the jumping velocity at the instant the droplet leaves the surface. As you can see from the results, we obtained a jumping velocity of about 0.38 meter per second, the maximum velocity for equal radii droplets coalescing and jumping, as well as for mismatched droplet size, that is one smaller droplet coalescing with a larger droplet, the jumping velocity decreased, and the highest jumping velocity was obtained when two droplets of equal radii coalesced. In terms of the direction of jumping, the coalesced droplet was always perpendicular to the plane of coalescence, and hence we got a jumping angle of 90 degree as a function which remains constant for the function of R2 and R1.